Okay, thanks. Okay, my name is Gaurav Prateek Sharma. I'm a postdoctoral researcher at KTH. And this presentation, I will dig a bit more deeper into the analysis of 5G delay. So the before the in the session before lunch, we Frank highlighted key differences and similarities between wired TSN switch and 5G system acting as a TSN switch, a virtual TSN bridge. But now I'll go a bit more deeper into the causes of these key differences. Uh, I would like to mention here that a large part of contribution for the material of these slides came from Joachim Sachs at Ericsson. He could not join us today, so I will be covering the entire presentation. So let me begin with what 5G promised. So 5G came with mainly three different flavors. So the classic enhanced mobile broadband. The objective was to achieve as high data rates as possible. Uh, the stress was not so much over the latency. Even if you have a good average tens of milliseconds of latency, that is fine, but should be able to transfer a large volume of uh, data per second. Then the second flavor is massive machine type communication. So here the stress is on connecting a large number of these low-cost devices over spanning over big area. And then finally the flavor of interest for us in this session and also in other sessions was ultra reliable low latency communication. So here we want to support what are known as time critical applications. So the requirement here is basically to have consistent low latency combined with very high reliability and availability. Okay, so what is actually the difference if we look at the delay characteristics of mobile broadband and URLLC? So, like I said, in mobile broadband, the focus was more towards achieving high bit rates, and the if you can say that the average latency that you support uh, is 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 within loosely within some range, that was fine. And if you have some packets that lie outside this range, that is not a problem. But when we come to time critical communications, it is important that a large part of delay distribution uh, is bounded. So, for example, if we have a requirement where we want 10 milliseconds uh, for 99.99% of time, so the a large part of the distribution would fall below this 10 millisecond delay target, and only a very small fraction, 1 minus whatever number corresponds to 99.999%, that percent of packets are allowed to exceed that 10 millisecond delay target. And then as the applications have their requirements end to end, so this latency plus reliability requirement should also be met end to end. And end to end would not only include the radio interface between the user equipment and GNode B, but also the core network. And sometimes there are networks that are sitting behind the core network, and as well as on the user side, there can be networks behind the user equipment. Like in our case, there can be a complete TSN network with lots of TSN bridges. So that further adds a few more hops in the end-to-end delay path. Okay, so as 5G is supposed to support variety of applications. These applications can vary in how much they require in terms of delay and reliability. So there is a provision to have special treatment for some kind of differentiation between how you support different traffic flows. So this 5G QoS flows allows having uh, different treatments to different traffic flows. So, depending on where actually the application endpoints are located, uh, the latency that can be induced uh, can be quite significant. So, for example, if you have applications that are sitting in a national some big region in a national data center, uh, the round trip time in addition to whatever you have in the on the radio side, these additional round trip times can be tens of millisecond. This can further be reduced by having more regional data centers, and then with edge computing, the latency can be further reduced to a couple of milliseconds. And if you have a local deployment where you have compute locally and your application, the other application endpoint just sits in your local area, then the latency contribution just because of the propagation delay is a sub millisecond. Okay, so coming more into local area deployment. So as we discussed that in local area deployments. To us, the interesting deployment is supporting time-sensitive networking with 5G. So there is already lots of standardization activities going on supporting this integration of 5G over 5G and TSN together. So a typical uh, very typical trade-off that is talked about when we talk about latency in 5G is reliability latency trade-off. So let's say we have a very good transmissions first transmission, so that there is a very high likelihood that the packet will be reached successfully in the first transmission. uh, uh, so we can bound the latency with very high probability. Let's say 3 milliseconds. At 3 millisecond, uh, we can say that this 3 millisecond target can be achieved with a probability of 99.999%. What we often see is that below this boundary latency, there is still a significant variation in latency. There can be several reasons to this variation, but one variation is frame alignment delay. So, what is frame alignment delay? So often the uh, transmissions in both directions, in uplink and downlink, they are organized in a what is known as a TDD pattern, time division duplexing pattern, where you don't always have opportunity uh, to uh, to send. So depending on uh, when the packet arrives, the arrival times of the pattern, and when is the next transmission opportunity, there can be some variation in the delay, and that causes this spread in the distribution even below the target that we want to achieve. And then in the cases when we don't have very uh, very high probability of successful first transmissions. there is a very efficient method of hybrid ARQ where we want to use redundancy in time domain. So we employ multiple retransmissions to boost the achieved reliability. And as you can guess, the problem here is that we can we have increased the average latency and also the spread uh, of the delay over a big range. The second important trade-off is reliability and spectral efficiency. So, as I said, the with more and more robustness in your transmissions, you can try to push this delay distribution to the left. So you can try to make your transmissions with very high probability that they will be successful by using uh, uh, robust modulation encoding schemes. However, as you can imagine, that this means to put lot more resources, lot more resource blocks in your 5G system. I mean, looking at how this varies as compared to mobile broadband. So the margins that you keep for such robust transmissions are quite high, so that you don't often have time intervals where you cannot support a particular data rate due to, let's say, uh, attenuation, a sudden attenuation, or degradation in signal quality. However, for enhanced mobile broadband, you set your operating point such that you can have multiple of these intervals where you cannot support uh, the corresponding data rate, but uh, you you uh, you enhance your reliability by having retransmissions during those times. So there is a complete toolbox for URLLC where you have set of optimizations that target delay and reliability both. Won't go into each of them in detail, but in a research project, there has been a quantitative assessment of how all of these tools in this LLC toolbox, they impact the delay. Okay, now let us look more systematically how uh, how different contributors uh, contribute to the delay in 5G. So overall, when you have some Ethernet that is supported over your 5G system, mainly three entities get involved from the 5G system's perspective. So in the downlink direction, you have your user plane function, so your gateway that is then connected to the G node B over the transport network, and then the G node B is connected to the user equipment over the radio interface, and this is where the most of the delay contributions are, and also the variations are coming from. So on the radio interface, you have a complete stack of protocols that have their own uh, contribution. So at the lowest level, have the physical layer and the MAC layer, and like I said before, the most of the delay variations that you see in the delay distributions, they come from the retransmissions due to hybrid ARQ, and then because your arrivals cannot be sometimes cannot be aligned. Uh, to the transmissions opportunity in uplink and downlink direction. So there is a delay and also corresponding delay variations because of that. Uh, you have a flexibility to choose different frame structures. So some frame structure would give you better delay, some would give you worse delay. Resource assignment. So how much resource block you give to particular traffic flows that would impact your the delay that you observe. And then if all the flows are have they all have same priority, so there can be contention for the resources, and there can be buildup of packets in the queues, and that can potentially increase the delay. And then in rare occasions, but important for some time critical applications, there can be a handover of UE from one cell to another, and that can temporarily cause uh, packet losses or huge delays. Coming to higher layers, so there is a possibility to have retransmissions also at the radio link control layer. So uh, if you have retransmissions, actually IQ retransmissions, they have failed to successfully uh, have uh, have a successful transmission, then there can be a retransmission at the RLC layer uh, that would also incur more delay. Okay, and then packet data convergence protocol. So PDCP is actually responsible for reordering the packets that may arrive at the receiver side out of order. So as individual packets can have uh, different delays. So if two packets that are sent uh, uh, consecutively, it could happen that the packet that was sent later arrives early because the first packet received multiple retransmissions. So the PTCP layer is actually responsible for reordering these packets on the receiver side, and to reorder you need to keep these packets in a buffer and wait for the earlier packets. So this incurs an additional delay. So now looking at what these delay actually look like, if we do some measurements on Unreal 5G setups. So on the left, you see the distribution for a commercial 5G network that is actually not optimized for uh, uh, time critical communications. So here you can see the minimum and the maximum spans over quite a big range, and also you have a uh, significant number of packets that experience a delay that is very different than let's say the average delay. And then for URLLC systems that are not that much commercialized, uh, but in the experimental setups, we definitely see a big improvement over the non-optimized deployments in terms of this minimum and the maximum, uh, and also the how much average delay that you can achieve. But as we saw earlier that the that even the delay variations that are in this millisecond range can be uh, uh, can be significant when we operate on TSN schedules that have uh, granularity of few microseconds. Okay, so packet delay variation. So time critical communications or time sensitive communication, what the objective here is that we want packets to be received at the right time. So should not receive it too early, should not also receive it too late. But 5G systems they introduce a lot of packet delay variations. This can be again problematic for end-to-end schedules. So a method that we also saw earlier uh, to correct for these delays is packet delay correction. So what we basically do is we use a dejittering buffer at the receiver side, and then we uh, we actually delay the packets that are arriving earlier than the target that we want to achieve. Okay, now I will go to the uh, a bit more quantitative assessment of delay. But before that, I will present this 5G delay decomposition model that we found to be useful to make sense of the measurements that we do. So on a very high level, the delay in both directions in downlink as well as in uplink. You have two major components: the delay in the core network and the delay in the radio access network. Core network for the industrial scenarios with local deployments, they have small average delay, and also the variations is not significant. And the interesting part is actually the RAN delay. So the RAN delay, we split it further. So we have first component in the RAN delay, that is we call it queuing delay. So the delay in the RLC layer. So this delay is made up of frame alignment delay, and also due to the packets that are already sitting in the RLC buffer waiting to be transmitted. So these two components, they contribute to the queuing delay. And then the link delay. So the link delay is whatever delay is below the RLC buffer. So first is segmentation delay. So segmentation delay is caused whenever you have uh, whenever you have times when you cannot send a segment one in one go. That could be because the for whatever reasons, the amounts of byte that you get, let's say because the resource blocks are not available, uh, that the number of bytes that you can get to transmit is less than your packet size. So you cannot send this particular segment successfully in one go. So you have to first send one segment and then another, and then maybe more segments, and the segment that is sent at the last has the highest delay, uh, and this additional delay is represented by the segmentation delay. Transmission delay includes whatever processing times you have, let's say at the if you're decoding the frame on the receiver side, so that is included in the transmission delay. And the retransmission delay, as you can imagine, is the delay is caused due to whenever you have unsuccessful decoding of a segment, and then you need to retransmit using hybrid ARQ. Okay, so uh, then this is the setup that we use to do the delay measurements. So our setup was based on open air interface 5G. Uh, so different hosts that were running this OAI functionality, they were all time synchronized using PTP. And then what we did was in the uplink direction, we were sending traffic, a periodic traffic with a fixed periodicity, 100 bytes, 500 byte size, uh, and we were timestamping these packets uh, inside the open air interface protocol stack in the UE side, in the base station side, and also at the UDP, the application endpoint on the server side. And then with these timestamps, we actually reconstruct the complete journey of each packet, and uh, uh, we can actually make comments about the individual uh, delay decompositions. So, I mean, this is how this the output from this tool look like. Uh, so I will actually discuss one of the optimizations that we were able to carry out thanks to this tool. So first on the left, top left, you see uh, delay distribution. So in particular, uh, complementary cumulative distribution function for delay. So what does that mean? So this means that for a given delay target, let's say at uh, 11 millisecond, the probability of exceeding this particular delay is 10 to minus 2. So that is how you interpret this CCDF. And then for each x-axis value, each delay value, we also plot what is the contribution, what is the in an end-to-end contribution of different components. So you have transmission delay, you have segmentation delay here, you have some queuing delay here. So what we found out, like without any optimization, you see, and then in the plot below, you see the different service times of different segments, and then also the time when the packet departs from G node B towards the UPF in orange. What is important to highlight here is that the packets uh, they were not being successfully sent in one segment, so they have to be segmented. So that caused a significant segmentation delay that you see in green here. So we could get rid of this by, let's say, giving more resources to this flow. And then in the plot in the middle, you see that the distribution has shifted to the left, and also the segmentation delay has actually disappeared. So all the segments, so all the packets were being sent in one segment only. And then we could also optimize this further by eliminating the frame alignment delay. So the frame alignment delay in our case is is represented in the queuing delay. So the delay coming at the RLC layer. So we could adjust the arrival times of the packets with respect to the uplink transmission opportunities. So we were able to significantly decrease the frame alignment delay, and then you see that the most of the delay that is left is coming from retransmissions, in particular at the higher delay targets. So this was mostly the delay quantitative and qualitative delay that we carried out. So I mean, in summary, as you can already see that the performance of wireless communication system, so 5G system, including 5G system, is very different than the wired system, both qualitatively and quantitatively. Uh, so although we can have a bounded delay at very small delay targets with a very high reliability, but this actually comes at a cost of spectral efficiency. So we have to use more robust modulation schemes. That means we have to put in more bandwidth, more resources. So maybe for time critical applications where we do not have that stricter requirement on average delays, but where we want to have very small packet delay variations. So methods like packet delay correction can be applied. And finally, with this uh, decomposition, and then using that decomposition to perform more advanced delay analytics. This can actually help in in supporting time critical communications on 5G systems. So yeah, that was my talk. If you are interested in reading further about the subtopics, there are some references included uh, in the slide set. Okay. Okay, I will be happy to take questions if we have any.
Thank you, Guru. Can you hear me? Does this mic work?
Yes, I can
Okay,
hear
perfect. Because then I can hand that on to someone in the audience, maybe, or if you have questions online, you can of course ask my teams. Is there any questions here from the audience in the room? So there is one question. So wait a minute.
Hi, thank you. A question here. In slide 15, you mentioned that you used hold time forwarding buffers for the jittering, the packet delay variation. Exactly. I was curious enough to know, how did you configure that buffer? Is it a universal retention time buffer, or do you timestamp maybe packets at the egress of the 5G system and you calculate a retention time? How does that buffer look like, or the configuration of it? Thank you.
So yeah, maybe Lucas or Frank would be a better candidate to answer that question. But from the proposals I have, from what I understand is that that the method of timestamping based dejittering is there in our proposal. I'm not sure about the other way that you talked about. So maybe someone who is maybe Lucas, if you have more idea about the other technique.
Yes, so what my current knowledge about this proposal is that you measure the residence time within the DATCOM node. So when a packet first enters the 5G system, you timestamp it, and by the time it arrives at the egress port, you take the difference of this timestamp, and then you can know how long the packet already spent in the 5G system, and then you can have a basically priority queue where you sort by the intended delay minus the residence time, and by that hold the packets until it reaches the intended minimum delay. So that's one proposal which we have about packet delay correction at the moment.
Yeah.
Of course, we have a follow-up question. Wait a second.
Just to make a quick comment on it, then you need to have a very good synchronization between UE and Gnode B so that you can timestamp that. Then how? Oh, a little bit of a feedback here. Then have you implemented this in reality, and maybe have you had this problem of desynchronization of UE and Gnode B, or this is just still an idea? Or we will discuss about that.
So we have a session about time sync in a second. I mean, it's maybe 30 minutes away, but maybe we can keep that question on the agenda, and then maybe Mahin can say something about it, because you will say a lot about this time synchronization in the 5G system. And yeah,
yes. So basically, the timestamping is possible to be quite accurate, but then you would require packet level timestamping that can be quite expensive. So if you want something that is a little cheaper to implement, let's say, you can also use virtual time slots, which are then more coarse-grained than exact timestamping. But then virtual time slots, and they basically induce some additional uncertainty, you could say. So just the time slot would then be in the range of microseconds. So let's say 20 to 50 microseconds. So then you have some sort of trade-off, but even that would then compensate the packet delay variation from a range of milliseconds down to microseconds. Exactly. Exactly.
We also have one more question online here.
Yeah, I'll have a look.
Is it me possibly?
Yes.
Hello, can you? Yeah. No, so I'm curious about this, the packet delay correction here. Isn't that really to protect a stupid application? Anything, wouldn't it be better to simply release the packet when they arrive and let the application make best use of them? A smarter application could simply also use packets that arrive earlier than expected.
Yeah, go ahead, Lucas.
So the problem is not only the end application, but if there is a longer wired network after the exit of the 5G system, then packets with a high packet delay variation can mess up with the schedule for the TSN network. And we will see that behavior in our next tutorial. So maybe we can, if the question still persists after the tutorial, we can go into further discussion there.
Okay, great, thanks.
Yeah, thank you. Any more questions in the online